Hi and good day everyone. I'm Harsha. Together with my team, we'll dive into two interesting questions from our BERT 1333 Advanced Electrical Circuit. We'll cover question C for transfer function and question F for BERT plot. So sit tight as we break them down and explore what they mean in the context of circuit analysis.
So this is our group members, which is me, Harith Ikmal bin Rahim, matrix ID B1224104559, and the second one is Muhammad Iman Zul Hakimi bin Muhammad Zaki B12241055, and the third one is Megat Zarif Irfan bin Megat Ahmad B1224105117, and the last one is Nur Hasha Inshirah binti Ahmad Nur Hishamuddin B1224104454. And for the team contribution, me, Harith Ikmal, will contribute to the derivation and explanation of the transfer function. The second one, Iman, will play a key role in the transfer function and BERT plot task in addition to assisting with formulating the transfer function. The third one is Megat Zarif Irfan, which is contribute to the analysis and refinement of the BERT plot result. And the last one, Hasha Inshirah, will focus on constructing and interpreting the BERT plot.
Here is a brief overview of what we'll be covering today. First, we begin with an introduction to the transfer function, followed by a look into the method, analysis, and result. Then we move into the introduction of BERT plot to understand the frequency response of system. After that, we go further into the analysis and result, discuss the finding in the discussion section, and finally wrap up with a conclusion.
Hi everyone, let me start by introducing the basic concept of the transfer function. The transfer function denoted as a h of s. It's a fundamental tool to find the frequency response of a circuit. It is defined as a ratio of the output signal ys to the input signal xs in the Laplace domain. In the simple terms, it tells us how a system processes an input to produce an output based on frequency. On the left side of the slide, we can see the standard form of a transfer function. Hs equals to ys divided by xs, where s is a complex frequency variable, where s is a Laplace transform of the output and xs is the Laplace transform of the input. Now on the right side, we highlight the key rules of the transfer function. First, frequency response. This is show how the system react to various input frequency. Next, pulse and zero. This come from the denominator and numerator and affect the shape and behavior of the response. Next, system behavior. This includes how the system amplifies and attenuates signals, shift pace, and whether it resonates or damps. And finally, impulse response. By taking the inverse Laplace of Hs, we can get system time domain behavior, which is useful in real-world analysis. So overall, the transfer function is a powerful method to understand and design circuit behavior, especially in control and signal system.
So next we will talk about method, analysis, and result of question C, which is h omega equal to 5 in bracket, j omega plus 2 for the numerator, and for the denominator is j omega in bracket j omega plus 10. And in this session, we will talk about the general state of equation to get the BERT plot, the magnitude BERT plot, and plot in the semi-log graph provided. And the third one is the phase BERT plot and plot in the semi-log graph provided. And lastly, we will determine zeros and poles from the question. So next, I will present about the method from the question given, which is h omega equal to 5 in bracket j omega plus 2 for the numerator, and for the denominator is j omega in bracket j omega plus 10. Equation given, this can be written using the standard first order term, which is a in bracket 1 plus j omega over a. For the step 1, we must express the numerator in standard BERT form. The numerator j omega plus 2 will be 1 plus j omega over 2, and for the step 2 is j omega plus 10, and if we convert it, become 10 in bracket 1 plus j omega over 10. So next, for the step 3, we need to substitute all into the transfer function, which is the original function given is 5 in bracket j omega plus 2 over j omega in bracket j omega plus 10, and we will become 10 in bracket 1 plus j omega over 2 over j in bracket 10 1 plus j omega over 10. From the equation I've said before, this can be simplified into 1 in bracket 1 plus j omega over 2 for the numerator, and for the denominator is j omega in bracket 1 plus j omega over 10. So as you can see, the table beside me is present a collection of fundamental factors used to analyze and construct BERT plots, which are essential tools for understanding the frequency response of control system. Each factor describes a specific component of a system's transfer function, detailing its unique contribution to both magnitude and phase characteristic. The table is organized into 3 main columns, which is the number 1 is factor, and the middle one is magnitude, and on the right hand side is phase. The factor column lists the mathematical representation of each transfer function component, and the middle one is the magnitude column specifies how each factor influences the system's gain in decibel, which is dB, while lastly the phase column describes its effect on the phase angle in degrees. So for the analysis, we will focus on 4 key factors, which is the number 1 from the table is constant gain K. The constant gain factor represents the system baseline amplification and attenuation. Its magnitude is a flat line across all frequency, calculated as 20 log 10 kdB. The phase contribution is 0 degree for positive K, or plus minus 180 degrees for negative K. This factor establishes the starting point for the magnitude plot and ensures the system's overall gain is properly scaled. So the second one, we will use first order 0, which is the number 3 from the table. These factor models are a 0 in the function, introducing a positive slope in the magnitude plot above its corner frequency. The magnitude increases at rate of 20 n dB per decade, while the phase rises asymptotically toward plus minus negative 90 n degrees. This component is particularly useful for improving system response speed or implementing lead compensation in controlling design. So the third one we will use is first order pole. The number 4 from the table, representing a pole in the system. This factor produces a negative slope in the magnitude plot above its corner. The magnitude decreases at 20 n dB per decade beyond, with the phase dropping asymptotically toward negative 90 n degrees. Such poles are crucial for modeling low pass filtering effects or system roll-off characteristic. And the last one, we will use second order pole, which is number 4 from the table. Number 5 from the table. This complex factor captures second order system dynamics, including resonance and damping effects. The magnitude plot shows a steeper negative 40 dB per decade, slope above the natural frequency, with possible peaking near for underdamped system. The phase contribution transition through negative 180 degrees, reflecting the system oscillatory potential. This factor is indispensable for analyzing mechanical system, electrical circuit, or any system with inherent oscillatory behavior. When analyzing a system, we begin by identifying all relevant factors from its transfer function. The constant gain establishes our baseline, while the poles and zeros shape the frequency response to construct a complete BERT plot. First, plot each factor's magnitude contribution individually, starting with the constant gain at the effect of 0, which increase the slope, and poles, which decrease it. The corner frequency mark where this slope change occur. For the phase plot, sum the individual phase contribution from all factors, noting where each begins to affect the total phase angle. The contribution of these four factors allow us to model a wide range of system behavior, from simple gain adjustment to complex resonant dynamics. By understanding how each component influences the overall response, we can effectively analyze system stability, design appropriate controller, and predict performance across the frequency spectrum. This systematic approach to BERT plot construction provides valuable insight into system behavior, enabling engineers to make informed decisions about design and composition strategies. Whether working with electrical, mechanical, or control systems, mastering these fundamental factors is essential for accurate frequency domain analysis and successful system implementation.
Okay, now I'm going to show you how to plot a BERT plot for a transfer function step by step, including both magnitude and the phase plot. We'll look at how to break the function into a simple part, analyze each part, and then combine them into sketch the final graph. The transfer function we work in is hj omega 5j plus 2 divided by j omega plus 10. The transfer function has a constant gain of 5, 1 0 at omega equals to 1 pole at origin and 1 pole at omega equals to 10. We begin with the constant gain of 5. To plot on a BERT magnitude plot, we calculate 20 log 10 times by 5 equals to 14 dB. This means the entire magnitude plot will shift it up by 14 decibels. Next, we consider the pole at the origin, which come from the 1 divided by j omega term. A pole at the origin causes the magnitude to decrease a slope of negative 20 dB per decade. So from the start, our plot drop with a slope of negative 20 dB per decade. Now, we add the effect of 0 at omega equals to 2. A 0 causes the magnitude slope to increase by 20 dB decade. So at omega 2, the slope change from negative 20 to 0. So the graph become flat starting at omega 2. For the step 4, pole at omega 10, the final component is the pole at omega 10. A pole at a slope of negative 20 dB per decade. So the starting at omega 10, the slope becomes negative 20 dB per decade again. In total, the magnitude plot has a decreased slope before omega 2, a flat section between omega 2 and omega 10 and decreasing slope again after omega 10. To summarize this, before omega 10, to slope is negative 20 dB per decade. With omega 2 and omega 10, the slope is 0. After omega 10, the slope is negative 20 dB decade again, and the entire plot is shifted up to 14 dB due to the gain of 5. Now we move to the phase plot. The phase is calculated as the sum of the phase shift from each part of the transfer function. Each zero and pole contributes to the phase over a range frequencies. We calculate the phase shift from each component. Pole at origin constant negative 90, 0 at omega 2 starting contributing plus 90 degrees between 0.2 omega to 20 omega, which is from 0.2 to 20 radians. Pole at omega 10 contributes negative 90 degree between 1 to 100 radians. So the phase change gradually instead of suddenly. The phase slope behaves like this. Start at negative 90 degrees to the origin pole between omega 0.2 and omega 20. The phase increase due to the 0 between omega 1 and omega 100. The phase decrease again due to the second pole. Finally, it settles around negative 1080 degrees at high frequency. So the final combined plot, we combine everything. The magnitude plot clearly show again the 0 at omega 2 and the plot and the poles at omega 0 and 10. The phase plot gradually transform from negative 90 degrees to negative 180 degrees based on frequency range. This is how we plot both the magnitudes and the phase BERT plot step by step. Okay, now we will discuss the discussion of transfer function. For the transfer function, it contains a gain of 5, 1 0 at omega 2 and 2 poles, 1 at the origin and 1 at omega 10. The gain of 5 increase the entire magnitude plot by about 40 decibels because 20 log of 5 is approximately 14. Next, the pole at the origin contribute a slope of minus 20 decibel per decade. This caused the magnitude to start decreasing immediately at the low frequencies. It also gives a constant phase of negative 90 degrees. Then, when omega 2, the 0 begins to act and adds 20 decibel per decade, which is cancel out the slope, so the graph become flat after this point. At omega 10, the second pole take effect. It adds another negative 20 dB per decade, it making the magnitude decrease again beyond omega 10. As for the phase, it starts at negative 90 from the origin pole, increase due to the 0, then decrease again because of the second pole. Eventually, the total phase approach negative 180 degree. In terms of system behavior, this is a low pass filter. It allows low frequency to pass the attenuation high frequency. The system is stable and the phase lag could affect performance in feedback control system. So that's all. The summarize of the key of the system from its BERT plot.
Now for introduction for BERT plot. It represents the frequency response of a system using two graphs, one for magnitude in decibel and another for phase in degrees versus frequency logarithmic scale. Its key feature is first magnitude plot represent how the gain or amplitude of a system output signal change as a function of frequency. And next for phase plot, represent how the phase of the output signal change relative to the input signal as a function of frequency. Lastly, cut-off frequency, the frequency at which the output signal power of a system, such as the filter or circuit, falls to a specific threshold relative to its maximum power.
Now, let's dive into question F word plot. The main objective is to obtain the transfer function corresponding to the given word plot. And in order to do this, we'll examine the question from three key perspectives. First, the method. Second, the analysis. And lastly, is the result. So let's go through step by step. Alright, let's dive into the question. First, we can see that this is a BERT magnitude plot because it shows that the gain h omega is in decibels versus angular frequency in rad per second. And to see some of the key features of the plot itself, from the frequency scale, we can see that the frequency is in rad per second and plotted on a logarithmic scale. And then the plot transition is at 10 rad per second and 50 rad per second. And then from the slopes, we can see that from 1 to 10 rad per second, the slope is goes up to positive dB per decade. And then in between 10 and 50 rad per second, the gain is flat, which shows constant. And then after 50 rad per second, the slope goes back to negative dB per decade. And from this, we can interpret that this is the BERT magnitude plot of a bandpass filter, because it shows that it amplifies signals in a specific frequency range, which in this case is 10 to 50 rad per second. And it also attenuates low and high frequency outside this band. Okay, from the possible transfer function form, a band pass filter like this usually has a transfer function form like in the slide. First, we can see that omega 1 is equal to 10 rad per second, which can also indicate lower cutoff. And then omega 2 is 50 rad per second, which can also indicate upper cutoff. And since we can see here k is constant, so we can use the formula of 20 log k equals to 20, because we can see that the amplitude of the graph itself is 20 dB. So to find k, we use the anti-log formula, and now k is equal to 10 dB. Alright, we already understand the question from the first perspective, which is method. Now we'll be moving on to the second perspective, which is analysis. We already know our k value is 10 dB, and then omega 1 is 10 rad per second, omega 2 is 50 rad per second. Hence, we just substitute all the value inside the function. I will get 5000 j omega over j omega plus 10 by j omega plus 50. However, since the gain at the center frequency is 20 dB, so we use 500 instead of 5000 to match and neutralize the magnitude response shown in BERT plot. Alright, to come to an end for our third perspective, which is the result. So we'll get, to match the graph actually, we get 500 j omega over j omega plus 10 by j omega plus 50.
Discussion for block plot. Firstly, the original transfer function has a zero at the origin and two poles at 10 radians per second and 50 rad per second. This structure is typical in filter or control system analysis and influence the slope behavior in the dot plot. And secondly, the denominator is simplified by multiplying out the fraction. Instead of keeping the complex form, jw over 10 plus 1 and close bracket and open bracket, jw over 50 plus 1 closing bracket. The expression is rewritten as jw plus 10 closing bracket and jw and plus 50 close bracket, making the transfer function easier to analyze. Third, the gain's constant k is determined from the given 10 dB gain using the formula 20 log 10 k equal to 10. We find that k is equal to 10. This gain is then applied to the simplified function. Fourth, the function become 5,000 JW over JW plus 10 and JW plus 50 after multiplying by 10. This shows that the full magnitude before adjustment reflecting the initial 10 dB amplification. Fifth, to match a Bob plot with 0 dB reference gain, the function is divided by 10 to neutralize the excess gain. This step ensures the transfer function align with standard Bob plot expectation, where the mid-band gain is normalized. And finally, the final transfer function is 500 and JW over JW plus 10 and JW plus 50. This expression clearly shows the 0 and 2 poles and is ready for the further frequency response analysis. Now we come to the conclusion of the presentation. This section summarizes the key takeaways and learning outcomes from the analysis and discussion presented earlier. First, we got develop a solid understanding of transfer function and their application in analyzing linear time invariant system. Secondly, construct an interpreted Bot plot to assess system frequency response, including magnitude and phase characteristic. Third, examining the influence of pole and zero and on system behavior, particularly regarding stability, gain margin, and phase margin. Fourth, strengthen theoretical knowledge and practical skill in control system analysis, essential for real-world engineering application. This outcome highlight the importance of foundational system analysis technique in both academic and practical engineering contexts. That's conclude our presentation. On behalf of Group 1, thank you for your time and attention. We appreciate the opportunities to present our work and hope it has provided valuable insight into transfer function, bot plot, and control system analysis.